Hello, 8th graders. In section 12.5, we're going to talk about symmetry. Now, you've done symmetry in the past, but we're going to talk about different types of symmetry in addition to just line symmetry. So a figure has symmetry if there is a transformation of the figure such that the image coincides with the pre-image. Now, there are different types of symmetry. The first kind of symmetry we're going to talk about is line symmetry. Now, line symmetry is, I'm sure, what you've done in the past. A figure has line symmetry, also known as reflection symmetry, if it can be reflected across a line so that the image coincides with the pre-image. So if we look at this heart, we can have a dotted line that goes right down the middle because that's a reflection symmetry. It creates an image on both sides of the line of symmetry that acts like a reflection. So the line of symmetry, which is the dotted line, is called the axis of symmetry. It divides the figure into two congruent halves. So if we look at example number 1, we're going to identify line symmetry. Tell whether each figure has line symmetry. If so, copy the shape and draw all lines of symmetry. So A, we have a trapezoid. Line of symmetry. Can you divide this into two congruent pieces? The answer is yes, and that's a really bad example, so let me erase that. So if you draw a line of symmetry, we would say yes, this has line symmetry. Now, how many lines of symmetry does this have? It would have 1. The next example, you could try to cut it if you wanted to. Try to cut it again, try to cut it. It doesn't work. So we have no line of symmetry. Now the starfish, there's 1. Let me redo that one. But we have another. We have another. And you can keep drawing them until you realize that we have 5 lines of symmetry. The next type of symmetry is called rotational symmetry. Rotational symmetry is when you can take something and rotate it. So a figure has rotational symmetry. It's also called radial symmetry if it can be rotated about a point by an angle greater than 0 and less than 360, so that the image coincides with the pre-image. Coincide means it lays right on top of another. Now the next thing we're going to talk about is the angle of rotational symmetry. Angle of the rotational symmetry is the smallest angle through which a figure can be rotated to coincide with itself. So if you spin something, and you can lay it on top of itself, the angle of rotational symmetry is the smallest angle which you can do that with. The number of times the figure coincides with itself as it rotates around 360 is called the order of rotational symmetry. So for example, if you took this square right here and I spun it, how many degrees could I spin it to get an image that coincides with itself? Well, you would only have to spin it 90 degrees. So the angle of rotational symmetry is 90 degrees because that's the smallest angle. Now, how many times would you have to move it 90 degrees to get 360? Well, 90 goes into 360 4 times, so we would have an order of 4. So let me just kind of show you how this works. If I took my box, spun it 90 degrees, there's the smallest angle which it can go onto itself. Another 90 degrees. Another 90 degrees. Another 90 degrees. I can spin it 4 times to equal a total of 360 degrees. So example number 2. We have 3 figures. I want you to tell me whether each figure has rotational symmetry. If so, I want you to give the angle of rotational symmetry and the order of symmetry. So can you, on part A, take this shape and rotate it so it lands upon itself? The answer is yes. So, give the angle of rotational symmetry. How many degrees would you have to spin that to land it upon itself? It'd be 180. Now, how many times does 180 go into 360? That means we would have an order of 2. Now, the M in part B, can I take this M and rotate it to land upon itself? Nope. We do not have rotational symmetry. And lastly, do C on your own. Pause the video and see if you can figure out C. Do you have rotational symmetry? Yeah, you do. Now, if I spun it, if I take that snowflake and you spun it, how many degrees could you spin it upon itself? Well, let's see if I can show you here. This snowflake here can be turned to give you this. So we only have to move it from here to here. Well, how far did I turn that? Well, you can count 1, 2, 3, 4, 5, 6. I could turn it 6 times because there are 6 different branches of the snowflake. So you can take 360 divided by 6. That gives you an angle of rotation, symmetry of 60 degrees. Well, how many times can you move 60 degrees to get 360? Well, it would be 6, so you have an order of 6. In example 3, you do not need to write any of this down, but let's show you how you can use rotational or line symmetry together in a biology application. In example 3, we want to describe the symmetry of each diatom. Copy the shape and draw any lines of symmetry. If there is a rotational symmetry, give the angle and order. So let's start with line symmetry in A. Well, line symmetry, I could draw a line straight across or up and down. So as you can see here, you would say, yes, we have line symmetry. Now, does it have rotational symmetry? Can I turn this so it lands upon itself? The answer would be yes. So you would move it how many degrees to land upon itself? 180, and then the order would be 2. In B, as you can see over here, line symmetry, we have 1, 2, 3 lines of symmetry. Now, the angle of rotation. How many times can I spin this to land upon itself? Well, I can spin it 1, 2, 3 times. So 360 divided by 3 is 120. So our angle of rotational symmetry would be 120, and our order would be 3. Other 2 kinds of rotational symmetry are as follows. We can actually use symmetry in 3-dimensional shapes. A 3-dimensional figure has plane symmetry, there's a vocab word, if a plane can divide the figure into 2 congruent reflected halves. So as you can see over here, we can take this prism, this rectangular prism, we can draw a plane right down the center and split it into 2 congruent halves. Therefore, that's plane symmetry. Now there's we can also cut it going the other way as well. A 3-dimensional figure also has symmetry about an axis. That means if we took this axis and spun it like a top, we would get this shape. If there is a line about which the figure can be rotated, it has to be greater than 0 and less than 360. So the image coincides with the pre-image. So for example, if you draw an axis right down the center of the cylinder, if we spun it, it would be on itself the entire time. All right, in example 4, our last example, let's identify symmetry within 3 dimensions. I want you to tell me if the figure has plane symmetry, symmetry about the axis, or neither. So can you take a plane and cut this 3-dimensional shape, this trapezoidal prism, anywhere that cuts it into congruent halves. Where could you cut this, or if you can? If you cut it, it does have plane symmetry. We can cut it right down the center. And therefore, this front half and the back half are congruent. B asks for an equilateral triangular prism. Does this have plane symmetry, symmetry about the axis, or neither? Can you cut this in half? The answer would be yes. You can cut it this way, straight across. So it does have plane symmetry. Does it have rotational symmetry? Which means, can I draw an axis anywhere that if you spun the axis, this prism would be rotated upon itself? As you can see, here's the plane symmetry, and the symmetry about the axis shows you where you have a line of symmetry. We can spin it or twirl, and by that I mean we're going this way or the other way. We can spin it so that prism will land upon itself. The vocabulary from this section would be symmetry, line of symmetry, rotational symmetry, angle of rotational symmetry, plane symmetry, and symmetry about an axis.